Alright, so in this video I'm going to show you how to model a problem like this, a beam problem. There is a cantilever beam here, so it's loaded at the end by this 1 kilopound force that's going down, and then a distributed force. You see it starts from 2 feet, point B, which is 2 feet from the left side, then goes all the way to the end. The cross-section area of this beam is 2 by 4. Modulus of elasticity is 29 million. Alright, so it says find the maximum, determine the slope and deflection at the end A. Alright, so let's see how we could do that. We have the solution, by the way, at the end result here from the theory, so we can use this to confirm our result. Alright, so let's see. Start the model. Alright, so we're gonna do static, we're gonna do structural model. Element type, we're gonna use beam 188. We're gonna make sure that the shape function order is cubic. So you do that here. So element behavior or shape function, it's gonna be cubic. And then material, you gotta come here, and then structural, linear, isotropic. Modulus of elasticity is 29 million. So I'm gonna use the PSI as my unit. So 29 million. Okay, Poisson ratio, we are not gonna need that, so I put that 0. Okay, section, you gotta go define the beam section. It was 2 by 4, so 2 is the width, or B, and height is 4. You can, if you like, you can look at this cross section, its properties. See moment of inertia, the area. So you can look at that. So we input that. Then we gotta model the beam. It's gonna use key points. One key point is gonna be at the, I'm gonna start from the left. Point A, I'm gonna put that on the origin of the coordinate system. So let me see. So we go here, point 1, 0, 0, 0, and then point 2. I'm gonna have point B as my point 2, which is it's gonna be 24 inches to the right. So point 2, 24 inches to the right, and then point 3 is gonna be point C, which is 5 feet or 60 inches to the right. So come here, point 3, 60 inches to the right. Alright, so then I'm gonna create lines from 1 to 2, from 2 to 3. Alright, so this is my model. Let's plot that. We can plot the lines. So these are the lines. If you like, we can show the nodes, the key points, line numbers, we can stick at them at the same time. Line 1, line 2, key points. Okay, then next is the meshing. I'm gonna just mesh. What I'm gonna do, I'm gonna just one element per line. So come here, manual size all lines, put here 1. For all lines I'm gonna have, just as I said, 1 element per line. Then next would be the meshing. So the mesh all the lines. Now let's look at the list. We can look at the, we can look at the elements. Have 2 elements, material just 1, sections 1. You see how the node 1 and 2 is for element 1, and then element 2 has node 2 to 3. Okay, so if you like, you can plot them here too. You can plot the nodes. What is that? Node numbers. Yeah, so let's look at the node numbers. You see them. Okay. So then next is applying the load. Alright, so the load, key point number 3 was fixed, right? So so pick number 3 is it's fixed, so I'm gonna have that. Oh no, I'm sorry, we are not gonna put a load there. So for fixing the support, you have to come under displacement. Alright, so come to key point 3. We're gonna fix that all degrees of freedom 0. Alright, so that makes it cantilever beam. So, and then we need to apply force. And that distributed load, you can apply it as pressure on the beam. So you go pressure on beam, and then if you remember from point B to C or node 2 to 3, we had that pressure. This distributed load, which is 1 kilopound per feet, if you convert that to inches, is gonna be 83. It's gonna be 83.33 pound per inch. So if you convert that, we need to do that. So and then the pressure is gonna be applied. You see, as you see, in Z direction, in negative Z direction. So so when I look at my model, you see the other force, 1 kilopound, is also the single force. It is the same direction. So when I apply it here on the model, you have to make sure that that force is in, when it's acting at that end. But plugging the number, you have to put FZ negative. So you have to put negative 1000 here to be in the same direction as my, the pressure or distributed load. Alright, so we are ready to run the model. Let's go here. Solution done. Alright, so let's see the results. There you go, read the results. No, I'm sorry, here. List the results. Nodal solution. We want to look at displacements first. Okay, so node 1 is point A. Node 1 has moved negative 0.34076, and which is, we have the result here for that one. You see 0.340, the solution, manual solution, we have it has 3 significant figures, which is matching. And if you're just looking at the magnitude, the magnitude is reported here. That's actually vector summation of ux, uy, and uz. Alright, so at point 2 or point B, we have it 0.158. The problem was not asking for that, so that's what we have. And then for the slope, you have to come here, rotation, vector summation, and then look at the the slope at the end. Again, looking at the magnitude is 0.79 times to 10 negative 2. That is matching our solution here, because you see 7.91 to 10 to negative 3. So the results are matching. That's a good thing. So one thing I want to mention is, if you're using just 2 elements to model this, it's very important to change the shape function here to cubic function. If you leave it at linear or quadratic, that's going to introduce error, because you know, that shape function linear is not enough. With the number of elements we have, is not gonna be enough. You can use linear shape functions, but then you have to have many elements introduced here. So you have to have it many, you know, you have to increase the number of mesh. Alright, so I hope this video is useful.